welcome back to the next hour here before we go over to the uh, modeling here. So I want to talk a little bit about the challenges that we are facing with modeling microgrids. I mean, as we already established, microgrids have a lot of benefits, but of course, they can also be a challenge when it comes to modeling. And I'm pretty sure most of you are going through some of these steps already. I mean, when you start a microgrid project, I mean, it's about the conceptual design. You have an idea, maybe you want to secure some funding, so some basic analysis needs to be done here to basically determine if a certain location makes sense for a microgrid. When you're over that hurdle, of course, a very detailed techno-economic design needs to be done, and this is what you're seeing today from Lulu and Rita, where we really do more detailed analysis, right? We think about the financial terms. Maybe we do a multi-year analysis. Maybe we already want to combine this with some power flow modeling, because the distribution system, the cables transformers are impacted by such a microgrid, and we want to assess on how they will need to be upgraded and so on. So, and then in the next step, when you throw over that hurdle, then a very detailed power system analysis might be needed, where you really do where you want to check if certain events might cause overloading for transformer cable. Maybe you want to do a fault analysis or whatever it is, right? And then in some instances, transit analysis might be needed, which means you, and most of the time this work is actually done by the vendor of the generator to figure out if the system is stable, if you would disconnect from the utility. And we as Xendee help you through 1, 2, 3. 4, we don't have it in the software because it's very specific to certain problems, and not every microgrid really needs a transit analysis. But we are helping you through the first 3 steps, which can be significant work. And the reason why I'm bringing this up is we did a project for the US Department of Defense a couple of years ago. And we basically established a process for designing a microgrid, but also applied it to certain projects in the United States and overseas. And we realized that 70% of the whole design process, 70% of the whole implementation process is actually around design, which is surprising because sometimes I have the feeling that people don't really pay attention to how you design a microgrid, the SCADA system, the economics behind it, and they just want to go directly to deploying it. But I mean, we have seen if you want to really have a microgrid which gives you the benefits that you were thinking, you need a very careful design process, which involves the steps that I have shown you early on. So that's my point. And this is actually also why we started the company, because 7, 8, 9 years ago, we have seen that a lot of people are focusing on the control of microgrids and new methodologies and all this, but not many were really concerned about a sophisticated approach on how to design such microgrids. And this is also why we want to help people here. So at the end of the day, from our perspective, this whole design implementation process should be connected to some extent, because you don't want to have discrete steps here which are disconnected. I mean, maybe you could do a conceptual design by hand in an Excel spreadsheet, but then when you go in a more detailed design, you need to do data transfer, you need to collect more data. Then suddenly you realize you have to do a more detailed analysis on the financing, and then you have a discontinuity here because your methodology maybe from the conceptual design cannot be applied to the technical design. And then even if you want to go further in power flow and all this, then how do you get the data from the economic part into the power flow part? Another disconnect that we want to overcome. And then, of course, when this whole thing is implemented, the control of the technologies in the field should be done with something similar that you had in mind during the design process, because otherwise you're ending up with different results. And we have seen this many times. Interestingly, people come to us and say, well, we already know the size of the battery. We already know that we want to have this generator, but we need a control system for this. And then we end up saying, Yeah, but we don't know if the control system actually gives you the benefits that you had in mind. Then we have to go back and actually do a simulation, see if the battery is big enough or maybe it's too small, it's too big, maybe the generator is in the wrong size and so on. So all these things, the design will then impact on how much you can achieve during the control. And this is why we link these two things. And you will see this from Lulu when she talks a little bit about how these products connect here. We can move from conceptual design, technical design into control and operation to make this a seamless process as much as possible. And the other thing is, what we also see with all these projects that we're doing, at some point, performance monitoring is important, and we do this for our controller projects because the performance monitoring tells you where you went off during your design phase, because you want to avoid this the next time to have better results. And this is why we have a feedback loop, which goes back. At the moment, it's a manual feedback loop into the design methodologies so that we can improve them if we find that we are overestimating, underestimating something compared to reality when we do the design. So that's why we have actually this process in place to give us better quality during design and then control. So a little bit about how we are doing this and why this can be a challenging process. So we are not only serving electricity, as already said, we want to also service heating, hot water, building cooling, or hydrogen. I mean, of course, we can just do electricity, but as I said, microgrids really live because there's this synergy between these different energy carriers and demands. So you have all these different demands here on the right-hand side. And then, of course, we have different options to supply those demands. I mean, simplest way is you just purchase the electricity or the natural gas from the utility, and you use it for your boiler or for your chiller or for your electricity demand. But there are a lot of different options, and they can actually compete against each other, or they can help each other. Let's take combined heat and power. Combined heat and power, let's say it's just an engine which runs on hydrogen, because we are renewable. We want to be renewable conscious, right? Environmental conscious. So we are running this on hydrogen. We generate electricity, but at the same time, we have also waste heat, which we can use either in an absorption chiller to cool the building, or we can use it for heating the building. But at the same time, a solar thermal system can also produce heat and be used in absorption chiller hot water needs for serving hot water. At the same time, photovoltaics is competing with the combined heat and power because it's generating electricity. So there are different technologies, and these different colored arrows that you're seeing are the energy flows. They are changing in every time step, because in one time step you have no output from the PV system, and you have maybe to purchase from the utility. Or if you have a battery installed which has enough energy in it, it can be used to power some loads, right? So it's a very dynamic system, and the width of these arrows is changing in every time step, because in one time step you might want to get more energy from utility or from other technologies. So when you size such a system, you inherently need to think about the operation of the system in the future, because otherwise you're not designing the system in the correct way. And this is where we differentiate ourselves from other approaches, because when we design the system, we simulate every single combination of operational behavior with different technology combinations to find the cheapest technology to serve your needs. And you might be surprised on how the technologies will be used in that way compared to how people are thinking they should be used. So this is also very important for educational purposes, because we have a lot of these conversations. Then why is the system doing it like this, right? And we see cases where, no, not the PV system is charging the battery. Maybe it's the CHP system, because you get a better system efficiency by utilizing all the electricity and wasted from the CHP system during the night for certain purposes and charging the battery with this, then oversizing the PV system in an area where PV is not that favorable. So very dynamic system and a very complex system to solve, actually. And the reality is there's no way in a manual process that we can solve this and find the best solution, period. it needs an optimization technology like we are using it. It's called mixed integer linearized optimization, which solves this problem automatically. And if you already have used Xendee, you will have seen maybe already that it can take a little bit to solve this problem, because we are going through millions of combinations here in an automated way to solve this problem, to come up with the best technology combination operational level. And this is what I'm saying here. When we design a system, it's not only giving you the capacity, but also for every month and period how you should run the technology. And here we have in black the electricity demand that was provided through the database, through an API, whatever it is. Then here in darker blue bars, we have the utility demand. And as you can see, it's pretty flat. And it's going away during the day because of PV, but it's really flat here because what it does is it does demand charge management. So it basically limits the maximum power that we're drawing from the utility, because in this case, there would be a power charge. Basically, the highest power demand within a month multiplied with a certain cost number can be $15 per kilowatt, constitutes a demand charge. So we're keeping that flat. At the same time, of course, PV is generating electricity during the day, which is just given because of the sun. But then here you see in the greenish bars, when the battery kicks in, you see it's kicking in the morning and the evening. But at the same time, you see this lighter blue bars, which is actually the CHP system, which is running almost flat all day long because of efficiency purposes and because of serving heating needs. And this now creates this benefit that we're actually charging here in the morning some of the battery, so that we have it before the sun comes up. And this is because we are utilizing the CHP system at high efficiency. And then, of course, we use some energy from the battery in the morning. And then, of course, when the PV is operational, we recharge the battery again. But this is a combination here between charging from a PV system and a CHP system. And I think that most people would overlook this, because in such a complex system, how should people know in a manual way, in combination with the heating side, that, oh, maybe I should charge here the battery in the morning, because if I charge it, I can utilize all the electricity, I have more wasted, and I can heat the building or whatever it is, right? So this is the complexity behind the system, which is really why it needs an optimization engine, a mathematical optimization, the background to solve this. And this is traditionally a very complex problem. We started this more than 20 years ago, and it was not easy to use. And the goal of the company and the software is now to make this easy to use, to hide all this complexity for the user, and making sure that it's easier to use by all these databases and processes that we have around this. And this is the last slide here regarding this methodology. And it's a little bit mathematical, but I think it can give you an idea on what we're doing here. Finally, in terms of how we do this, there are two basic things that we consider. One is the objective function, which sets the objective, what we want to achieve with a microgrid, and the other one is the energy balance, and there are some basic constraints. The energy balance is very simple here. It basically says that the demand plus the losses in every minute time step, what it is, needs to be equal the generation plus the purchase, period. And the generation, of course, could be coming from PV, from whatever it is. But those are variables. So the generation of variables and the purchase of variables, but we know what the demand is. And now what the tool is doing, it's trying to figure out what generation we have to install and how to run it to balance the system, and at the same time minimize our objective function, which means the costs are the cost for purchasing electricity, the tariff, the cost for purchasing fuel, the cost for carbon if we're in a carbon market, the investment cost for certain technologies, the operation and maintenance costs minus what I'm selling back to the market, right? And now we are minimizing this function, the objective function, by varying all these different capacities and operational levels so that we can minimize the costs and at the same time fulfill the energy balance. And that's what's done in an automated fashion in the background that you're not seeing. And this is why when you run when you run an optimization, you see something like 200 equations have been considered at the top, or how many millions variables it went through, because it's actually testing for you all these combinations to minimize the costs and fulfill the energy balance. And of course, there's certain constraints like around investments or there are constraints around the financing, what is the interest rate, what is the how much you want to finance from third parties. All this goes also into this model, together with technology constraints like is there any self-discharge of the battery? How quickly can a generator respond to load changes, right? All this stuff combined with climate constraints or regulatory constraints goes into the model and gets solved for you, so that you get the capacity optimal one and also the operational level. And if I think we heard something like this morning from infeasibilities, and the challenge, of course, is sometimes we can define data which creates some challenges for the algorithm, which means it cannot solve it because there's not enough energy in the system. So let's say you have a constraint on the point of common coupling, which doesn't allow you to purchase more energy than, let's say, 100 kilowatts, but your demand is 200 kilowatts, and you're not allowing any technology investment, then you will get an infeasibility. And this, I think I also saw an email around this yesterday. This is where we can help you, but it can be a little bit tricky if you set some of these constraints in a way that the algorithm has no way to solve this for you. That's basically what it means when we get an infeasibility. So I will talk about the University of California, San Diego. It's actually an EV microgrid project, so some of you will like this. Briefly, I will talk about the naval base here in San Diego, because interestingly, they wanted to build a microgrid without the need to upgrade the distribution system, which then they did. I have this Puerto Rico one, but maybe I'll let my colleague speak about this, or participant about Puerto Rico, because he might have more information about this. I will show you a very interesting case from Europe, which is a residential building, and show you how we can how we can implement the microgrid control at really very low cost and an effective way. And then I will talk again about UC San Diego, which is about model predictive control, because as I said early on, if you design such a system, you also want to make sure that you can control it in a smart way, because otherwise you're not getting the benefits that you were planning for. So when it comes to UC San Diego, UC San Diego is one of the oldest microgrids in the United States, maybe, and maybe you know about this, because research started here 15 years ago, and it was really a nice place for research. It has a lot of distributed energy resources, PV batteries, fuel cells, a lot of on-site generation in form of steam turbines and gas turbines. And it's almost a 60 megawatt facility. So it's a large facility. As I said and showed early on, it's one of the prime markets for microgrids. And they already have some basic electric vehicle charging. It's not much. It's just 46 level 2 chargers, so basically 11 kilowatts, and some DC fast chargers up to 50 or 60 kilowatts, which means they could cover 2.5 megawatt hour per day on EV demand. But now they wanted to upgrade the system in a way that they can have 40 additional DC fast chargers with 125 kilowatts. So some significant fast charging. And the idea was really to figure out where to place these chargers to avoid infrastructure upgrades, so that we don't have to upgrade the cables or transformer, or just in a minimal way. And on the left-hand side, you see now the topology of the system, the high-level topology, where we see also where the EVs are installed, the PVs, the batteries, and all these technologies. Now, what we are doing is we are modeling this with power flow in a so-called multi-node fashion in Xendee, which allows us to not only come up with the best distributed energy resources to minimize our costs and reduce the purchase from the utility, but also the places where we want to actually install these technologies, right? And that's what we did with Xendee. I have a movie about this. I'm not talking about this in all the details, but you can actually watch this later on. But at the end of the day, what we have here on the left-hand side is the reference case here, this pie chart, and the right pie chart is what we did. So on the left-hand side, you see in this brownish area a lot of energy coming from DG, basically gas turbines and steam turbines. There's some little PV part, and there's then this purchase, this blue one from the utility. What we are saying is, if we, in a smart way, upgrade the distribution system and also place new technologies, we can have way more renewables, and way less purchase from the utility. And this creates now a situation which I have on the next slide here. So the baseline is the current situation. Currently, they're spending almost $26 million in annual energy costs, including CapEx costs, which they already had. OpEx cost is the biggest part here. And the revenue from selling electricity to EVs is pretty minimal because they have only 4 DC fast chargers and this level 2 chargers, so not making money. We ran now different cases here. The first one was just upgrade the chargers in a smart way, these 45 or 6 fast chargers, and place them so that we're not burning the distribution system, but don't upgrade the distributed energy resources, okay? And you can see that already with this, we are reducing the cost, but it's only because we're selling more to the electric vehicles. You can see that we have now 4 million revenue because of the electric vehicles, because we're selling electricity, but we're also purchasing more energy and power from the utility, okay? Because we're not installing new technologies. So we're actually increasing our exposure to utility, and that's probably an issue because, I mean, we have to upgrade some BCCs and whatever it is. So now if we say, let's also upgrade the distributed energy resources together with optimally placing the chargers, we can see that we're now bringing down the total annual energy cost to almost $22 million because we're bringing down the operational cost. We're purchasing less from the utility. So my point here is, by installing a microgrid, we don't have to upgrade the distribution system, the local one. We can offer more services to the AVs at lower cost than just relying on the utility. And I think that's really, I mean, an important case for microgrids when it comes to electric vehicles. And this is the model within Xendee. It's a so-called multi-node model where you can see that we modeled the different pockets here. So you see in orange the cables, you see also some transformers. So that's a very sophisticated model, which we're not showing you today or work with you on today because Rita will just work on a single node model to show you the basics about Xendee. But here we model all the different loads, the existing battery systems. We provided where we want to have options, and then Xendee basically solves this for us and tells us where to place the PV in this. This is one sensitivity around where to place this new PV. So it exactly tells us, hey, on this node, on this node, on this node, and this node, and this node, you should put this PV system so that we can avoid the upgrade. If it's practical, because if you have the spacer, so we need to model this and we can do this in Xendee, but my point here is you can strategically place the technologies and also the chargers. They're all now going on one bus so that we actually can provide this additional service at lower costs and actually also at lower carbon emissions, as you can see here. And if you want to watch on how I did this, you can actually go to this YouTube link and watch it. I think it's a 10-minute movie. So the second case that I want to show you here is let's go through this very quickly. It's just really a naval facility here down in San Diego, a very old one. And it's a training facility. So the sailors need to go through training here before they get deployed. So they have critical buildings here for simulation, for certain kinds of simulation here. And they had to basically come up with a microgrid which can sustain a 14-day outage if the utility goes down, right? And they had two options. They could upgrade the distribution system or they go with a microgrid. And we figured out with them that it's actually cheaper to build this microgrid than upgrading the infrastructure. And there were also practical reasons. Since it's so old, they actually didn't have the plans anymore where all the cables are. So it would have been a huge undertaking. And this is why they segmented the system and actually installed a microgrid, which can now sustain also a 14-day outage. And this is just a result. I can skip over this, but it basically shows you a typical result and how you would approach this in terms of net present value and what technologies you should install at different assumptions. So this is Puerto Rico. And as I said early on, this is a project that we did, I think, 2 years ago with Idaho National Lab. And it was really to figure out if we can create energy resilient communities in the middle of the island, because a lot of those microgrid projects were focused on coastal areas because of all the tourism there. but there are a lot of mountain areas which are underserved, and they need also to sustain hurricanes. And this is why they were thinking if they can build local microgrids for every community, which can power shelter buildings or warehouses for refrigeration so that nothing gets spoiled here, in combination with upgrading this hydropower plant. To my knowledge, parts of this are getting installed now, but because of the challenges that we faced regarding the utility, I'm not sure if now the hydropower gets updated, but maybe one of the participants knows what's going on with those hydropower generation nodes out in Puerto Rico. But my point is really, you can really nicely create microgrids which are also linked to larger generation resources and can help service underserved communities in the event of problems here. Okay, so I have two examples left, and then we can go into the modeling. So this is really just, so we did this project to really showcase that we can also, at low cost, achieve a lot. And this is a residential microgrid which has a PV system, a battery, and an electric vehicle which is used as secondary car for commute. I think it's around either 6,000 kilometers, 6,000 miles a year, something like this, right? And all the communication for this control system was established with equipment which you can purchase off the shelf. It's wireless, it's power LAN, which means you can communicate over the distribution system. I'm not sure if we use this in the United States, but it can be used in Europe. And a Raspberry Pi for $100 was used to control this system, right? And so the whole installation, the control system, was around $3,000. It doesn't include, of course, the PV and the battery because it was already installed. And the $3,000 is for the Pi, the metering equipment, and the communication. And the control strategy is basically to minimize the sales from PV back to the utility, because we have sales prices in this case of 7.5 cents. So if I sell electricity, I only get 7.5 cents for a kilowatt hour. If I purchase, it's around 35 cents per kilowatt hour. So the goal is really to avoid selling back to utility and not purchasing, because you're getting hit with this high cost, right? And at the same time, you have now an electric vehicle in this mix, which you want to charge. So actually, we want to schedule when we charge this electric vehicle, if it's connected, so that we don't end up with higher costs. And this controller runs on a 1-minute basis with AI-enabled forecasting for the electricity load and also for the renewable energy output. And just to give you an idea about this, I mean, this statistic is from last year. So from January 1st to October 15th, the total energy cost was $75 for this electric vehicle, which includes this electric vehicle, which goes 6,000 miles a year. And for 3 people, this is a household with 3 people, all the cooking and all the electricity. At the end, we ended up at $250 to $300 because December, of course, there's less solar radiation. But I mean, if you think about it, I mean, here in California, we end up paying $500-600 a month for electricity and natural gas. So this is really a nice way to do it. And this is how it's done here. So you see basically a forecast here for the PV output and also for the load output. And note how volatile the load is. This is a residential building. So electric cooking is basically involved. And you can see actually here someone, when this seems to be breakfast time, or here's some breakfast and there's some cooking. So very volatile. So a huge challenge to predict this. And now we have the electric vehicle. So for these next 3 days, we knew that the electric vehicle might be plugged in because it probably was over a weekend. I can't remember, but it basically now schedules the charging of the electric vehicle in a way that we are never depleting the stationary battery and that we are never purchasing from the utility or selling back. And here in this bluish line, we have the plan for the EV charging. So you can see that it would charge during the night, but then here this orange line is the state of the charge of the stationary battery. You see it's never going below 10%, which is the minimum state of charge. So it realizes, oh, I have to wait here with the charging because I know for some certainty that we will have this load and this output. So when it reaches a certain point, it can start charging the car again. it has to stop here because it cannot go below 10% here before the sun comes out again. So it's a very predictive methodology to actually achieve our goals here. And we call this model predictive control. And the last example that I have here is again around UC San Diego, which has a more sophisticated control. But I mean, this is just interesting because we are dealing here with a 4 kilowatt system. The load can go up to maybe in winter to 7-8 kilowatts with all the cooking. But even for such a small site, we can predict to some extent the load, the output, and run it in an efficient way. So this is now the concept of a model predictive controller. So in the middle here, we have the optimization. Okay, so this is the same methodology like we use it in Xendee design, it just deals with real-time information and only with the dispatch for the next couple of days. We need a physical system integration, meaning we need to have a communication with the underlying inverter, battery, electric vehicle charger. It can come through the cloud, or we directly connect to this so that we can measure what's going on in the system. With those measurements and historic information, we can do load forecasting and PV forecasting or renewable forecasting. So we actually predict for the next 3 days what the load might be and the output might be. With those information, in combination with electricity price information, constraints on the technology, how much fuel we have on site, we optimize the system in terms of dispatch, how we want to use the technologies to basically minimize our costs. So we are creating a operational curve for the next 3 days on a 1-minute basis based on this information and send it down to the physical system, asking the technologists to follow these set points for the next minute. After a minute, we repeat this whole process with new information, create a new dispatch profile. And in this way, we can create an adaptive behavior which foresees some changes, which means we can run our technologies differently with this information because we know that the weather is changing or maybe the load is changing. This means we can prepare ourselves. And with such a forward-looking system like we have it also for the residential building in Europe, we can actually save a lot of money. And that's what I'm going to show you here. Okay, so this is UC San Diego again, and it's a complex control problem for microgrid because we only have PV, batteries, and the utility, which means we have no generator here to stabilize the system. And if we have such a forward-looking control system, we need to be really good in forecasting. Otherwise, we might create bigger issues for the system if we forecast the wrong output from the PV system for a long period of time or the load, because then we might run out of energy. And then the energy needs to come from the utility system. And then we might hit really expensive periods and we might end up with higher prices. So that's really a challenging control problem. And here we are riding on existing hardware controllers. So we basically have already a hardware controller for microgrid in place, which does some basic functionality. But on top of this, there could be a software-based controller with, like this one with an MPC, which is called MPC, to do the forecasting and the smarter prediction. And this works because of different electricity prices, for example. And this is why I said, most of the microgrids really benefit from this cost management. So if you run a microgrid in Africa for electrification, then you don't have this complexity and you have different objectives for a microgrid than what we have here, for example, in the United States. So we have almost 90 cents per kilowatt hour for electricity during on-peak rates. At off-peak rates, we have 6 cents. So there's a huge spread, which we want to utilize because we want to make sure that we somehow charge the battery at low cost or discharge the battery at high cost, because this is net metering. So when the electricity price is high, we also have a good chance to get a lot of money for selling electricity, right? So we want to manage this. The same is true for power charges, demand charges, 17 cents per kilowatt. If we can flatten the demand, we can save a lot of money. And the existing controller doesn't have forward-looking capabilities, doesn't know these prices, and this is why it's limited. And this is why we are deploying this forward-looking MPC, which helps us to estimate the impact of changes in the operation so that we can save money. But of course, such a controller also has some uncertainty attached because we need to do forecasting. Forecasting comes with errors. And there are some cases where the error might be bigger than the savings that we have because of our energy arbitrage. And this is why it's important to simulate the benefits of such a controller before we deploy a controller to make sure that it's really working. And here's a result for UC San Diego. At the bottom is what the system would do without us, and this is 100% accurate because it's a rule-based controller. We feed the virtual twin here with simulation with the same forecasting data that goes in the real system, and then it basically mimics what it would do. And you can see here we would end up on this day with 74.31 kilowatts of electricity purchase. The controller flattens this because it knows when we can bring it down with the battery that we have and the output to 24 kilowatts. The other thing that's happening here is, and this gray line is basically the utility purchase or sales, right? And you see here at the bottom in the reference case, we start selling because it's negative back to the utility when the battery gets full. Here in gray, you can maybe still see the PV output, and here the state of charge of the battery in dashed. When it becomes full, we start selling. But that selling is not coordinated with the electricity price, which means we might sell at periods where energy is not that expensive, which means we're not making money. This is why in the controller, we defer this to times when the expensive period starts and we make more money. And this constitutes, in this month, 80% cost savings through an MPC compared to an existing hardware controller. And why is it that I'm showing you this? Because our design methodology assumes we have a smart controller, because otherwise, I mean, we're not getting the benefits that we need from the microgrid. So when you simulate a microgrid, you should better use the same methodology at the end for controlling it. There are some products out there which already do this MPC, but my point is there's a huge connect between operation, sizing, and reality, and this needs to be taken care of. And I have one slide left. Maybe there's still some questions, and then I will hand it. Well, then we have a break, and then I hand it over to Lulu. Okay, so one slide, because it's important for today also, what data is needed for a basic techno-economic analysis here. And the first thing is you need to describe the existing situation. The existing situation could be you have already existing technologies. Maybe there's a boiler. Maybe there's already a PV system. So you need to describe this in a way that the model can handle this, and we help you with this. Maybe basically saying how old is the system, how big is it, and something like this. Tariffs. All these microgrids really live from cost management. So defining the existing situation in terms of tariffs and estimating the future changes in tariffs will be important if you do a multi-analysis. We help you with this through interfaces and APIs to collect this information, or we can do this for you, but that's a very important driver for a microgrid, the tariff. The weather data, of course, it should not be up on you to come up with the solar radiation at this location, the temperature, so we will all bring this in through databases. Then, of course, the other very important driver for microgrids is the load data. Because, I mean, we have to balance the load, right? So we need at least a year of data with a 1 hour time step. So just having an average demand for a quarter or for a month will not do it, because at the end of the day, the load pattern in combination with the tariffs will determine how much you can save, right? So that's also something which is important, sometimes a challenge. And then when you have this, you actually think about the options that you're interested in. I mean, are you interested in a generator? Are you interested in a PV system, battery system, hydrogen? You just basically drop those options on the screen, and you will see this later on, and you can take from databases some data. So now you're telling the system, hey, I have this existing situation, I'm interested in these technologies, but I want to know what is the best technology combination and operation level to minimize, for example, my costs. And for this, we also need to provide some financial constraints, interest rates, and all this. But then the optimization will solve this for you automatically and tell you, you need this capacity for this technology, and you can expect those operational levels or behavior to achieve this goal. And you can do sensitivities around this.